I represent Shape Architecture here in Denver. We are a 9-person practice, and we are focused on sustainability, community. We do projects across the region, primarily in Colorado. And yeah, we're excited to talk about this project. Here's some glam shots of us in our office. These are just, we work again across the state doing various types, building typologies from single family to nature centers, hotels, and various other things. There's a really great conversation about sustainability and community in the last spot today. And I think one of the points was that sustainability has a really broad definition and incorporates a number of different values. And these are, I guess, some of the ones that we value both personally and professionally in our work. And a lot of these we feel overlap with the Passive House standard.
That would be me. So I'm Peter Stewart with Sterling Builders. We are the owner, developer, and builder of the Ogden Street duplex. And we were working with an architect when we started and realized when we wanted to go passive that we needed to work with a group that was passive. So that's how we got involved in this. We worked with Shape and we worked with EMU Building Science. And yeah, that'll get us through that slide.
Okay, here's our site. It's Google already updated it, which is nice of them. There's a 6-lane highway just to the south. It's a pretty tight lot. You can see the surrounding context. There's a lot of other duplexes, triplexes, fairly dense housing. I would say, what do we call it, a challenging site?
Yeah, challenging. I think when we purchased the lot, there was really no intention of building passive on it, but we realized pretty quick we wanted to because of the lot. So the lot sort of drove, if you can build a passive house in this lot and it works, the proof of concept is exponentially better than if you can build a passive house in the middle of a field. It's going to be quiet, it's going to be green, it's going to be clean air. We got dirty air, we got noise, we got all sorts of city pollutants, and we're dealing with all of them through building a passive house.
Yeah, I think that's a great point. I think other sites, wouldn't lend itself so much to the standard, just in terms of, like Peter said, the acoustics and health inside, indoor air quality, all of that. So we actually, obviously tried to make it work to our advantage. Again, here's kind of just like the overall site plan. Obviously, we have great solar orientation. The zoning forced us to have the access of both of the units off of the east. And then, so obviously, again, it's a very tight lot with a pretty urban building form. Here's just a quick layout. The south unit is on the right side, north is on the left. The party wall dividing the two. Reference. Another thing that really had working well for the site was a couple of the deciduous trees running along the south side of the lot. So that was really our shading strategy. We really wanted to be careful with the amount of glass we were putting on that side, both for hitting the standard, but also for the acoustic problems that kind of come with the window versus the super insulated wall. So those trees actually helped a lot in terms of the modeling, but also for the kind of indoor light quality. We even actually added some interior windows. There's a kind of opaque window there in the stairwell where we tried to bring light into adjacent spaces without taking the penalty of the glass on the envelope. So here's the detail of the party wall separating the two units. One thing to talk about too is the roof assembly. This is a non-vented, all cellulose, dense pack roof. The air barrier is sitting on the underside, and then there's a service cavity below that. This is, technically it doesn't meet code based on having an actual vented assembly. Working with EMU, we were able to address that via a WUFI model, but that's something that's we've been working to get around, obviously, to reduce the use of spray foam in our assemblies. And there's this tricky detail on the right. It's very easy to draw, but much harder to build. I don't know if you want to chime in on that.
Yeah, so when we came at this project, we came at it from a single family perspective. We're a single family builder, and we got into multifamily. The largest building we've ever built is 2. So we're talking single family twice. The way we look at it, very different than what these guys are doing. And the biggest challenge that we had was, how do we get a passive house envelope to scale or to cover over the top of our firewall? So what we did, it was a pretty straightforward detail. We designed it on site with Shape and with Emu, and we sealed with a bunch of products from 475. We sealed right over the top of our actual firewall. So code requires that I can't put anything flammable in my firewall. I said, great, I'm going to touch it to the top of it. And then they say you have to take it to the bottom of your sheathing. And I said, great, well, I will put this infinitely thin layer of air barrier between the top of my firewall and the bottom of my sheathing. We ran it by a bunch of different people, and nobody complained. So whether or not it's code compliant, we were talking about a 32nd of an inch. And we did that, and it worked great, and we were able to get air tightness. We don't have air tightness between the units, not to a passive house level, but we do have air tightness between the units to a standard building level. There is air leakage between the buildings, but being that both sides are passive, you don't really have a pressurized system to force air between the 2 units. So the roof assembly for this, we did scissor trusses. We had a 18-inch heel, and I think we're about 22.5 inches at the peak. You can see in that picture where we have dense packed fiberglass insulation on the top of our Martello. So being what Morgan was talking about earlier with that unvented roof, we needed to make sure that we could dry to the inside of the roof. So we did so by dropping Martello on the bottom of the scissor trusses, and then we installed a 2x4 service cavity on the inside. The area that you can see that is dense packed was the area that we could access. The rest of it is over that staircase, so we ended up just putting bats on top of that. But that service cavity really doesn't matter in terms of whether or not we have what insulation we have in there whatsoever. It was not part of our model. It was just additional insulation. We were hitting about an R82 in our roof, service cavity included.
And just to note on the wall assembly there, we have 2 inches of EPS over a 2x6 wall. So that's about an R29 or 30, I think. And again, with the single families that we're doing in this climate zone, we're above 40. So it's a pretty dramatic drop in terms of insulation cost, just going from that 1 building to 2, essentially 2 houses. Here's some fancy graphs that Enrico did that kind of walk us through how we approach that unvented roof. Is he here? Enrico, are you in the room? No. How convenient. He really kind of came at it. We presented the idea to him. He was very much in support of it, and his belief is that building science from the vented versus non-vented is very outdated, especially in terms of these high performance envelopes. And so he was able to help facilitate this assembly here. Obviously, the install of the cellulose of that dense pack becomes way more critical, and where that kind of air barrier is compared to or where it sits in the sandwich of that assembly.
So we had skylights that we installed on both units. The unit on the north side that didn't have that direct sun exposure, we put a much larger skylight on, and we did that mostly for light purposes. We did certify the whole building as a unit, so it was 2 units, but we blower door tested them together, and we certified them together due to our air tightness challenges of that firewall. But there is no southern exposure on that north unit, and there is another duplex or triplex right next to it. So getting a very large passive house skylight in there was our best bet. We were looking at about R value of 10 on that skylight, triple pane fixed skylight. So we were able to achieve our passive house envelope and get solar gains through that on that north unit.
Generally, south-facing skylights in Colorado are a pretty terrible idea. So, when we did this, it's obviously aligns with that kind of 3-story staircase to let that heat kind of dissipate into the house. that was like a pretty critical way of getting that solar gain into that back unit.
This is Morgan walking up the stairs. So I think what you can see there is that is our interior wall. So we did insulate between the units, and that was more due to the rating of that fire assembly and due to sound. But there's no real thermal necessity for thermal breaks between the two units. The other side of that wall has hopefully 68 degrees, just as this side does. So it is insulated. We insulated between the floors for sound as well. But you can see where on that dense pack fiberglass wall, that was our exterior wall, and that's what we were shooting for, that roughly R30.
And you'll notice the plywood on the floor.
Okay, so this was a detail that I don't know exactly how I came up with it, but I didn't come up with it personally. I just found it. So this is a detail that I found in JLC when I was looking for cool things that we should do in a passive house. And slabless slab being one of the coolest. I could say it a dozen times when people would say, "What's a slabless slab?" So that's pretty exciting and get people interested, and nobody quite understands it. But right here, what we did is we made an insulated concrete slab, but we removed the concrete. So if I was to put down a concrete slab, I would have to put either sleepers or a plywood raft on top of my concrete. So I would go gravel, insulation, concrete, lumber, plywood, hardwood flooring. And what we did is we just deleted the concrete out of it completely. When you put foam, all of this foam that we use is rated to go under a concrete slab. It's rated to go under a foundation. It's not high density foam or anything of the such. It's not structural foam. It's just straight up EPS foam. And when you do 2 layers of plywood over the top of that, and you pull your air barrier between your foam and your plywood, you get a super rigid slab. And we were crossing our fingers and hoping it would work. It worked great. We have some non-load bearing walls, partition walls bearing on it. No settlement, no sagging. The hardest part about it was making sure that we got that dirt level or the gravel underneath it, because if that gravel is at a level 1/8 of an inch, that will travel through to your floor. So your floors will go up and down. So we were able to fine tune grade that by changing our aggregate size as we went up. But this is the detail we did, and working around the details of how we take the air barrier from between the foam and the plywood up to the walls was a little complicated. I think we have, there we go. So we sort of had 2 different details. We had one at this interior wall, and we had one on the exterior wall. So the interior wall was a footer going directly into wood, and the exterior wall was a footer going into a concrete stem wall. In order to jump that gap, we just attached, so we glued and taped our plastic to our footer, installed all our foam, and then rolled our plastic straight back down to it. So we actually jumped from one unit to the other through the footer, through the structural concrete footer. So these are some pictures of, you can see on the left side there, that was us trying to get that gravel level. So it kind of looks simple and it looks pretty straightforward until you add 10 plumbing penetrations. You're inside the building, so if you're using heavy equipment, it gets pretty rough. So those were the dilemmas we dealt with. Stacking our foam was very fast, very simple. You can see the plastic rolled up on the wall. So that plastic there is connecting to the footer, and then on the interior wall, that is rolling through the footer and rolled up the other side, so that we have our continuous air barrier moving through the center of the building using our concrete footer. Perfect. Yeah. Yeah, I'm done. Yeah. Okay. You guys have seen plywood before. So in order to address the air tightness of this house, this is the ERV system that we put in. I don't think we spent a lot of time in our structural portion planning out where these tubes were going to run, but we did some sort of on-site moves and adjustments to be able to address that. So we did open web trusses, except we had a bunch of structural headers that were stopping us from running our tubing through that. So you can see in that photo on the right, we dropped underneath our beams in order to make space to be able to get those to all rooms of the house. Still going? Perfect. So we did a preliminary blower door score. We were about 0.56 or 0.58, something like that. and we were pretty upset because we didn't want to meet the code. We wanted to make sure that we had a number that we could challenge against other people's numbers. So we're builders, we're competitive, and we want to build something better than you. So that's difficult. So we spent a lot of time. We actually smoke tested the building twice, pressurized it, smoke tested it, found probably 100 leaks. We had framers that had framed with a couple of sheets of zip, removed it, and replaced it. So there were hundreds of nail holes through individual sheets of zip. We were able to get down to 0.28 for our final blower door score, which used to be close to the tightest in Colorado, but I think somebody beat us, but not multifamily. So one of the other cool parts about this project is as we progressed, the building kept changing colors. So we started off, we had it framed, it looked like wood, and then we put zip sheathing on it, it turned green. Then we put zip tape on it, it turned black. Then we put white foam on it, everybody couldn't figure out what we were doing. Then we put black membrane on it, that's a WRB membrane, and nobody could figure out what our finished layer was. And then if you go one more forward, maybe, do we have one?
Another one.
Maybe, of the exterior?
There's one.
Cool, so then we slapped a bunch of thermary wood on the outside, and at that point in time, I think people were pretty sure that that was what we were gonna do. No more layer changes, so yeah, that's our project.
Thank you, guys. That is a fabulous project, and I would like to also note that this was a winner, both in the details category, and then it was shortlisted in the climate category for this project, for this year's Passive House Network Design Awards. So our next team consists of a tried and tested team that's been cranking out multifamily passive houses for quite some time, and I'm going to hand it over to, all right, Louis, Dylan, and Ryan.
Okay, hello. I'm Ryan Lobello from Handel Architects with Louis Koehl. He's our Director of Sustainability. And Dylan Martello, he is the Senior Building Solutions Consultant from Stephen Winter. Handel has opened a Denver location, and I'm heading that effort with my colleague Katie, who's in the front row. And so one of the main motivations for me coming to Denver is that we want to bring Passive House at scale to Colorado and the surrounding states. So many of you in the Passive House community know us, but for anyone else who's new, just real briefly, I'm going to do an introduction and then we'll jump into a case study. So we specialize in residential, hospitality, student housing, mixed use, offices in New York, Boston, San Francisco, Hong Kong, and now Denver. And we specialize in making well-designed buildings that are impeccably laid out with their unit planning. We are also sustainability specialists. We pride ourselves in being leaders and trendsetters for sustainable design across North America. Passive House is a main part of that. We're also doing full electrification, mass timber, geothermal on our projects. We like to help our clients push their boundaries and create exemplar projects. Dylan, luckily, let me do his intro slide. So I'll say Stephen Winter Associates, they are kick-ass consultants. They do sustainability, lead, Passive House, inspections, commissionings. I'm always amazed at the scope that they offer us, and it's always done impeccably well at a very high level. And the Stephen Winter and Handel Architects team, we've partnered together on 6 large Passive House projects, 4 of which I'll share with you guys today. So these are those projects. A brief summary. On the far left is our first. It's the house at Cornell Tech. It's 270,000 square feet, 26 floors. When it was completed, it was the world's tallest and largest Passive House. It's now since been surpassed. It's graduate student housing in New York City. It won Lead Project of the Year almost as an afterthought, because once we did the Passive House, we were happy. And then we submitted the paperwork and voila, Lead Project of the Year. Next project is Sendero Verde. It's a 3-building, 2-phased project, 700 units of 100% affordable housing. Shout out to Adam Watson. One of our clients is here. And this project really ticks all the boxes as an architect. It's 100% affordable housing. It has a really robust podium of community facilities and nonprofits. It's community gardens. It's well integrated, from a program and architecturally, like contextually, to its neighborhood. It's really fantastic. And it's a huge Passive House certified project now. The phase 1 is open. Residents have moved in. And phase 2 is going to be completing in Q1 of next year. The third project there is Winthrop Center, Boston. That's a 1.8 million square foot mixed-use building, of which the kind of bottom 21 floors is a Passive House commercial office space, the largest commercial office space, 700,000 square feet. And then we just opened on Wednesday. Was that yesterday? The retail space, and so like now the entire building is open. And then far right is UTSC, this University of Toronto Scarborough dormitory. It's an undergraduate dorm. It's actually the same size as the house at Cornell Tech, 270,000 square feet, but only 9 stories. There's also a fully active dining hall that is within the Passive House volume and is fully electric. And so that's a big thing to note. And so one thing you'll notice from these 4 projects is that the Passive House standard is very flexible. There is no style of a Passive House. Cornell Tech was a metal mega panel. Sendero Verde is a brick and ephes project. Winthrop is a triple glazed curtain wall assembly. And then UTSC is a stick-built metal panel. So Passive House allows us to meet all of our clients' varied goals and their individual project requirements. And then this is the result from an energy use. On the left, you have a code-compliant business as usual case in New York City, 118. On the right, you have Sendero Verde, that's a 15 EUI. And so I like to just take a big picture, look at this, and like before, you have almost 50% of your total energy going to heating and cooling. And then after with the Passive House, it's 10%, but also look at the size of that pie chart. It's a much smaller pie. And it kind of begs the question of what are the next things that we need to look at, domestic hot water and plug loads. And not on this chart, another thing we're looking at is embodied carbon as well. And then when we started with Cornell Tech, we were interested in Passive House because of its energy savings. But very quickly, we were focused on energy reduction, but then the Passive House is so much more than that. It's the health and wellness of a Passive House is where we're starting to see a lot of resonance of these Passive House concepts, the resonance with like the general public. And 24/7 filtered fresh air, consistent temperatures, fantastic acoustic separation. That image in the bottom in the middle there, I love this image. This is the Cornell Tech this is our 15th floor. It's eye level with the Queensboro Bridge. And just think about that. New York City, rush hour traffic, twice a day. How noisy is that, right? When you have a airtight, well-insulated facade, you shut the window, you don't hear a thing. Your home is your sanctuary. It's perfect for mental health. And it kind of demonstrates how Passive House is ideal for these urban environments to help create a sanctuary, a home for many people. In Sendero Verde, it's 100% affordable. I think that project, not only from a point of view of leading from a size and scale of Passive House, but in terms of equity and sustainability, it's a leader in that. It's showing in New York City, we can do Passive House for institutions like Cornell Tech. We can also do it for affordable housing. We can do it. Why can't you? And then this is a third one. We talked about energy, and then we talked about health and wellness. A Passive House is also a resilient building. A wildfire in Colorado on a Monday can result in horrible air in New York on a Thursday. And so when we're doing filtered fresh air in our buildings, your clients, your residents, their health is better. This is another main area when we're talking to folks in California about Passive House, and we're talking about ERVs. They don't know what to do with an ERV, but like we say, oh, but what about wildfires? This will help you with that. And all of a sudden, their ears pick up. They start listening then, and they're very interested in Passive House. There's also temperature and survivability in terms of resiliency. And so there's an example, the Ken Sobel retrofit Passive House up in Toronto. So there was a study that they did before they retrofitted. They shut off the the energy to the building, and within 2 hours, the temperature dropped inside below 55 degrees in winter. And then they did that same study after they retrofitted it to Passive House, and it took 2 days. Okay, so like usually within that amount of time, the grid is back up and running. So it shows how the Passive House is resilient in that regards too, and kind of combating these kind of weird climate events. And then this slide is about marketing and leasability. The two images on the left are not Handel Architects projects, but I love what they're doing. It's the Candela Loss and Flo Chelsea. They are marketing on and leasing on their health and wellness. It's all about the 24/7 filtered fresh air. You go to their websites as a prospective tenant or renter in these buildings, and that is their main marketing push. I love that. I'm gonna use it too, you know. And we're starting to do that with our projects as well. UTSC, the campus, they love this as well. It perfectly aligns to their mission. It's about a physically healthier space for their students, and it's about they're really focused on the mental health. And it's an area that's great for their current students as well as their prospective students. So they're trumpeting this. And then Winthrop office that you can see here, the full 21 floors, that's where the balconies are. That's the Passive House office area. It's been fully leased in this market. I'll say that again, in this market, that building is fully leased up in office space. And it's because Passive House aligns so well with many companies' ESG goals, like that we have differentiated. Because we're Passive House, we've differentiated ourselves in the market, and then we're fully leased, while other buildings that may be new and not at this level are sitting vacant. So I'm not gonna read all this. On the right side is basically to say that across the country, codes are becoming more strict. I wanna focus on the diagrams on the left. We believe the bottom one, the kind of gradual implementation is much preferred to the abrupt change of the upper left. And so our Passive Houses in New York are going to comply with some of the most strict emissions limits in 2050, once assuming the grid is clean. But like we much rather, you know, gradually implement these across our portfolio rather than have to make wholesale changes right away. And that's from an architect's perspective, talking to our clients and the builders as well. They much rather learn piecemeal how to do this rather than all of a sudden have a lot of change. And so it's in your interest to start now, comply now, or you're gonna have to do a very expensive deep retrofit later. And so like that's part of the financial argument, and I heard that reiterated with some of the folks in earlier panels as well. And then back to the 4 project comparison real quick. These are very dense buildings. They're in different climate zones, 4, 5, and 6. And at the very bottom, you can see the energy budget. You can see Cornell Tech was designed to 38.1. And then PHI's density calculator, they're learning from these large scale projects about how to determine what your energy budget is. And it's just, so with Sendero Verde, you can start to see the difference. We're getting up close to 50 EUI there. Winthrop Center is an extremely dense building between 9 a.m. and 6 p.m. and then it's vacant. So there's a different kind of project challenges there. And then UTSC's traditional dormitory with suites, you can just see how dense that floor plate is. And it's also in Toronto, which is climate zone 6. And so you can see why we're up at 70 EUI. And then, so as you're approaching projects in different locations, these are kind of the 3 main things you want to look at. And when you're determining your energy budget, these are impacted by what climate zone you're in, what is your typology, and what is your density. And then, as we all know right now, Passive House has clusters in the Northeast and the Pacific Northwest. And as you'll see in there next with Lewis and Dylan, there's a lot of opportunity for Passive House between the coasts. Lewis is going to start to show you now how we can start to really fill in the middle of this map.
All right, thanks everyone. Yep, I'm Lewis Koehl. I'm the Director of Sustainable Design at Handel. Love being at the Passive House conference. It's really exciting that it's in Denver, hearing all these Denver voices. And you know what's happening in this community is really, really thrilling. So as Ryan mentioned, you know, we see kind of a concentration on the coast, particularly in the multifamily space. We think this is largely due to kind of codes and incentives that are happening in these communities, which we'll talk a little bit more about later. So we've been looking in several other areas around the country, doing kind of early stage feasibility studies about how we might bring this to different markets. And Dylan is going to dive into the really interesting stuff here, where we're going to take one of our projects that Ryan mentioned and drop it into the city of Denver and into San Francisco, and see what taking a large multifamily passive house west looks like in terms of the model. So I'll kind of jump through here. So the project that we're going to look at is one that Ryan mentioned there, Sendero Verde. So this is a really exciting project that is near completion. It's built in 2 phases. There's building B, which is the 2 smaller buildings that you can see there, north and south, and building A, which is the tower. It is, as Brian mentioned, 100% affordable. It's designed as a community of opportunity with a wide array of community partners you can kind of see listed there. The idea being that residents not only have an affordable place to live, but also access to a lot of essential services on the site. This project, we've done a handful of more detailed presentations. I'm going to give a very high-level overview just to contextualize Dylan's study here. But if you're interested in a more detailed dive, there's something that we've done for the Passive House Accelerator, which is, of course, a great resource that I'm sure everyone here is familiar with. And Dylan did a great tour of the project. There's a video of that at the end of the slide. We'll have a QR code that you can follow to see some of those resources there. So we're going to take B South, which is the smallest building here. It's 85 units, about 90,000 gross square feet. And that's going to be our sample project that we're going to look at here in New York, and then we're going to drop it into Denver and San Francisco. As I noted, it's 100% affordable, a wide range of area median incomes from 90% AMI down to 15% for those formerly experiencing homelessness. The site is in East Harlem in New York City. It's on the Manhattan grid, so it's not quite aligned due south, slightly off axis here. I threw these mean temperatures down here in the bottom corner, and this is for New York City. The max 62.6 degrees and the min 49 degrees. This is not the most relevant thing to Passive House, but it's just to kind of contextualize the difference between these environments, which you'll see here in a moment. So the exterior wall at B South, as Mark mentioned in the presentation earlier today, a lot of concrete in New York. This is a block and plank building. Precast planks, CMU block is the structure. It is an EFIS exterior wall, and we used EPS insulation there. Didn't quite have mineral wool systems ready for deployment there at the time of detailing here. And then we have an interior layer of insulation with a foil facing. We have the kind of primary air barrier there is the blue line. That's the waterproofing membrane. And then the green line is the vapor control layer, which we need because we have insulation on the inside of that air barrier, and that's kind of required by the climate. You can see the kind of specs there that we end up with. And, this is really not, this is pretty conventional construction. It's really, as we're all learning, Passive House is not reinventing the wheel. It's really just really paying attention to the details, making sure that all your contractors, subcontractors, consultants are on the same page here with the goals, and getting excited about the performance. The window performance there, U value of the center glass U value is at a 0.1. We have UPVC windows, which is something that we haven't really used on projects before. We use them here because we were able to get a much better U value. We use them on the low-rise buildings, but on the high-rise building, it still wasn't quite there in terms of the testing. So there we are using an aluminum system. There's a shot of the interior there. The light-filled interior, everyone says the small windows, but it's a pretty nice space. The heating and cooling system is a VRF system. The condensers are on the roof. There are closet units in each apartment, and then they have they ducted air to the bedrooms and the living rooms for the heating and cooling. The ventilation is supplied separately, which we'll touch on here in a moment. Looking at this, you see some pretty long refrigerant runs. Lois mentioned in her presentation earlier today, and Sarah mentioned in the multifamily presentation yesterday, that is something that we're thinking about a lot with VRF. I think, we'd like to try to figure out how to move to more hydronic systems and get away from all this refrigerant, but that's where we are at the moment. Ventilation is handled by a centralized system. It's, with ERVs on the roof and supply and exhaust ducted to each unit. Here's just a quick glimpse at the model. Again, Dylan is letting me do his slide here just for the sake of expediency. But the main thing to take a look at there is the primary energy demand at 46. That's not the 38.1 that we would typically see for our climate zone. It's been adjusted for density, as Ryan noted. The other thing to note is the air tightness at 0.4. So we were, targeting a 0.4 to get a little more buffer. So we're going to take a look at two sites, one in Denver, here in the Lohi neighborhood. And you can see the kind of mean temperatures, just for the sake of reference there. The max is a few degrees higher, the min is a few degrees lower. We're dealing with much larger swings here in Denver in climate zone 5. And then in the second site is in San Francisco, in the Soma neighborhood. Max temperatures at 66, min's at 51. So not really getting to that same degree of cold temperatures there in San Francisco. Again, that doesn't tell the whole story, but I'm going to let Dylan kind of take over here. Thank you.
Okay. So as far as kind of digging into a comparison of the climates, so what we're looking at here, if you would focus on the top graph, this is heating degree days and cooling degree days for the three climates: New York City, Denver, and San Francisco. Heating degree day, cooling degree day, for those that aren't aware, is essentially you look at it on a daily basis, the average temperature for that day, and you do a subtraction of the average temperature for that day from what the base temp is. And in this case, the conventional base temperature for climate analyses like this is 65 degrees Fahrenheit. However, as Lois mentioned earlier in her presentation, we think for passive house buildings, it's actually not 65. It's probably more like 55, maybe even a little bit lower for heating. It's essentially that balance point at which the exterior temperature needs to fall to where you need to turn on your heating system, and then vice versa for cooling. So, so we looked at base temp 65, but then we also looked at base temp 55, which we think is a little bit more appropriate for a passive house building. And what you can see here, a couple highlights. So New York City, you have a good amount of heating degree days and cooling degree days. In Denver, somewhat similar, though we're going to talk about humidity in the next slide and how that plays a role. But you can see there's more heating degree days in Denver. So there is actually more of a sort of heating demand than New York City. And then in San Francisco, it's actually much lower on the heating side and on the cooling side. So it's just a much easier climate to design in. When you look at base temp 55, which again, as I mentioned earlier, we think is a little bit more appropriate for passive house, you see that balance between heating and cooling get a lot closer. And in the case of New York City, it's actually a little bit more cooling degree days than heating degree days. So take it with a grain of salt. This is, we're just doing numbers, math basically. So there's a lot of variables that play into this, but we have to focus, I think, in New York City, both on heating and cooling and humidity. In Denver, a little bit of heating and cooling, but more heating than cooling. And then in San Fran, they have it easy. All right, so as far as humidity is concerned, this graph is showing the ASHRAE 1% design dew point temperature. So without getting too into the weeds here, this is a way to just sort of assess how much humidity and moisture is in the air, and thus how much dehumidification load the building's gonna have to sort of realize. Now, as far as the actual numbers concerned and what that means, don't get too hung up on that. The key is, one, if you notice, San Fran and Denver are lower, and that's actually by a substantial amount. A 10 degree, 12 degree difference in exterior design dew point temperature is very different. So it's much more dry in San Fran and Denver. If you look at New York City, it's very, very close, if not exactly the same as Atlanta and Jacksonville. So southeastern climates. So New York City is really, really difficult to design in, and the humidity is a big part of that. And that's something that we're digging into, and we actually have some monitoring on interior humidity and temperature in the Sendero Verde project as well. So that's exciting and should have some really interesting results by next year on that. So what we did is we took Sendero Verde, Building B South, we picked it up with our crane, and we plopped it on those sites in Denver and San Fran. And what you're seeing here is a representation of the 4 main criteria for new construction passive house buildings: heating demand, cooling demand, air tightness, and PE demand, and representing that as a percentage of the threshold. So what you're seeing is the modeled results from this pick up and drop, and you're seeing that it represented as a threshold. So 100% means that the model is just passing the threshold or just meeting it. If it's above 100%, it's over the threshold, that's not passing. If it's below, which we obviously want, it's passing. And we like to pass with a little bit of buffer. We know that things happen in construction, so we like to give ourselves a little bit of buffer. But what you'll notice is that in Denver, which is the orange bar, the heating demand is over the threshold when we pick it up and move it. So we're gonna have to address that. You'll also note in San Fran, the heating demand is way low. So that is a sign that maybe there's some optimization we can be doing to make the building more cost efficient in that climate, which we know, as I mentioned before, is a lot easier in terms of climate conditions. So one other factor here, you'll notice the cooling demand is much higher in New York City than Denver and San Fran. So even though the cooling degree days in Denver are somewhat similar to New York City, the humidity component, that's a large reason as to why, is that humidity will result in a much more higher cooling demand. And then the last thing I want to focus on is that air tightness. When we design a building, we always assume the absolute worst case scenario from an air tightness perspective, meaning it just passes the blower door test. So that's 0.6 ACH50 for new construction. So as a result of that change, if I jump back and forth here, the zooming thing is being weird, but there we go. Okay, cool. So you can see it jumps up from about 120% in Denver on the heating demand side with the tested ACH50 of 0.4 up to about 130%. So we're gonna have to address that, as I mentioned there at the top. So this is sort of our climate optimized design or more optimized design, which I'll get into in a minute in terms of how we got there. So you'll notice that one, we're passing on the heating demand with in Denver, and in San Fran, we sort of relaxed the building's design a bit to still meet the heating demand thresholds and all of our other main thresholds, but now have a more cost optimized design as well. So what did it take to get there? So as far as the building's envelope is concerned, we needed a little bit more R value in the wall. So the laser pointing is not working very well, but we go from an R34 wall in New York City on average to an R39 wall. So that's translating to about 2 inches more insulation on the EFIS system. As well, we have in San Fran, or I'll stick with Denver first. So as far as the slab on grade and actually elevator pit walls, which is essentially where the elevator core kind of runs down a little bit below grade, we had to add 2 inches of insulation to get it to R12 at those walls. We had to increase the roof R value a little bit from R36 to R47. And then windows are basically the same windows. We didn't really make much of a difference, just a slight change in U value. So we're probably looking at maybe a better coating selection on the glass, but it's still a very good or great triple pane window. And then the center of glass solar heat gain coefficient, we raised from 0.38 to 0.47. We want to be cautious with that. We don't want to raise it too high and then potentially exacerbate overheating concerns. So that's what it took to get the Denver heating demand to pass that threshold. In San Fran, as I mentioned before, we were able to really relax those criteria. We didn't have to add any insulation to the slab or in the elevator pit walls. We were able to use much more code-aligned levels of insulation as a result of that. And the other big highlight here is on the windows in San Fran. We went from obviously a triple pane, very good triple pane window, to just a fairly average double pane window at a 0.31 U value in BTUs. And then a 0.27 solar heat gain coefficient. This is meant to really keep the overheating potential as minimized as possible. And then here at the bottom, you can see just sort of the starting point with the New York wall assembly that Lewis walked through earlier. And then in the Denver and San Fran scenario, we assumed a steel stud wall, which is much more common in places outside of New York. New York is really one of the one jurisdiction that has a lot more block and plank and concrete CMU-based construction.
Yep, Dylan, if I can just note that because of that, the exterior wall, even though there's more insulation in Denver, it's narrower because you're able to get a higher R value out of that stud wall than you would in the CMU wall. So that is something that is a challenge in New York that you don't face as much in Denver. So you gain a little bit more floor area, even with more insulation.
Yeah, that's a great point. As far as HVAC is concerned, so what we've added here in this graph, the only real new information is the last row, and that's the ERV and HRV efficiency. So in New York City, obviously, we have an ERV with a sensible recovery efficiency of the unit itself of about 86%. We're going to need the same system, essentially. In Denver, that 86% range for an ERV is probably the highest we can get for a large-scale central system that can meet the ventilation loads of this building. So we're kind of peaked out at 86%. One thing that's interesting, in New York City, we need an ERV to keep the moisture out of the building in the summertime, which helps keep our cooling loads down. In Denver, the ERV is actually there to help keep moisture in the building so it's not too dry on the interior. So ERV, for different reasons, if HRV does typically get a little bit more efficient when you don't have that enthalpy component to it, but the benefits of the ERV over HRV really outweigh the HRV in New York City and Denver. In San Fran, it's a little less critical because just the climate's just a little less challenging. And we don't need as high of an efficiency, so we were able to get away with a 75% efficient ERV. But really, in San Fran, the benefit of the ERV is really it's less about the energy benefits, and it's more about the indoor air quality, health benefits, helping keep smoke out in wildfire smoke events, helping have continuous filtered fresh air that's balanced fresh air into the building. So that's really one of the main benefits of the ventilation system in that case. Okay, so the last thing we looked at was the elevation variable, so particularly in Colorado. So what I wanted to do is take, again, this sort of climate optimized design, which is that orange bar off the left, which we just walked through, was the sort of Denver design criteria, and take it at an elevation of 8,000 feet. So obviously in Denver, we're about 5,000 feet. Take it up to 8,000. And then also take it up to 10,000 and just see what happens to the model. And what you can see is that going to those higher elevations, we nearly doubled or even greater than double our heating demand. Obviously, there's no cooling demand. We don't really have to worry about that. Primary energy demand did increase as a result by a fairly decent amount as a result of the heating demand increase. So how do we sort of deal with this? This is kind of a tricky design challenge. One of the things that I wanted to note was that the PHI classic threshold may be much harder, if not really difficult to achieve at those higher elevation climates. So I wanted to show the low energy building thresholds for the heating and cooling demands, which are about twice as high as the PHI classic threshold. So if interested in certification for a building at this high elevation, the low energy building threshold might actually be more appropriate. But at the 10,000 elevation level, what we looked at, well, actually for the 8 and 10,000 was if we were able to reduce the air tightness of the building from 0.6 ACH50 down to a very optimistic, but maybe achievable 0.2 ACH50. So again, maybe that's a little ambitious, but just to see the effect as a result of that. And that actually did allow the building to pass at the 10,000 foot elevation. So we saw a reduction from being about 50% over the low energy building threshold to now just passing the low energy building threshold as a result of that. One other aspect of this as well is potential for quad pane windows. So I did take a look at that, and that did result in a slight reduction. It wasn't as impactful as the air tightness. It was probably about a third as impactful as this, but another consideration to make as well for those higher elevations. We're thinking ski resorts, that sort of thing, or just generally multifamily type housing at those higher elevations. So yeah, there's a lot of factors that play into this, and heating demand is a challenge at those higher elevations. So I'm going to hand it back over to Ryan here to summarize and wrap.
Yeah, and I'll just say that Cornell Tech, when we did the blower door test, it was at 0.15 air changes an hour. So the 0.2 isn't out of the question. It does take a lot of effort.
Right. Yeah, that was an extreme effort. Yes. Good point.
So looking at this, a lot of us here are focusing on the right side of the equation. We're designing and building more energy efficient buildings. But the left side is vital. The utilities and governments, they have to meet their targets too. The grid has to go to renewable sources. Otherwise, our efforts here on designing our energy efficient buildings are not going to have the intended effects. And so everyone in this room, everyone at this conference, we have to advocate. Reach out to your utilities, get on these panels, get on these boards, talk to them, hold their feet to the fire, and make sure that they meet their clean grid targets. It's in all of our interest to do that. The next one. And then at Handel Architects, and I don't want to speak for Dylan, but I think you probably agree with this. We see passive house as like the foundation towards getting to a zero carbon future. As energy codes are becoming more strict, passive house is becoming the new standard. And I used to say in 10 years, but maybe now it's some time has passed. I'll say in 5 years. We may not be calling these passive houses. We may just be calling them buildings because the codes are catching up. And so passive house plus low embodied carbon, electrification, and a clean grid, that's how we do this. What we do today at this conference will become the baseline for how we build in the future. And as you've seen from all the fantastic projects at the conference, we know how to do this. So let's get out there and do it. Thank you.
Thank you so much, gentlemen. That was fascinating. So I get the honor of getting to ask some of the heavy questions here. And the first one I'm actually going to ask is to Dylan. Just a quick question as to why did you use the primary energy, the old PE framework, and not the PER?
Yeah, that's a great question. So the reason why was because when the building Sendero Verde was designed, we didn't have all electric domestic hot water systems available. So as a result, we just had a high efficiency gas condensing boiler plant to service the domestic hot water loads. And as a result, when you have really any amount of gas use in a passive house building, you cannot meet the PER criteria because the hit as a result of the site to source factor for gas is too steep. So we had to meet the primary energy or PE threshold. Yeah, but we would look at PER if it was an all electric building.
Nice, thank you. So we've looked at two different projects at incredibly different scales. One built and one hypothetical.
We built it in New York.
You did build it in New York, absolutely. So I'm going to sort of start out, I'm going to go into the details first, and then I'm going to go out to sort of more the meta discussion about how do we scale multifamily out west here. But I'm going to go first to the question that is always asked, costs. So starting with the SHAPE project team, what were the costs compared to, say, a multifamily? Were there any benefits to kind of duplexing? And I know we've sort of discussed this, so I want you to be candid about it. And did the duplex forms translate into those any cost savings compared to conventional single-family homes? And either of you who would answer that.
Am I on now? No one believes architects when they talk about cost and money, so it's probably better that you take this one.
Go, Peter.
It's because they have no idea what it costs. So we started off building our project, and we had ambitious goals. We were trying to do this on a cost-effective basis, and we sort of shifted midway through. We were looking at like $200 a square foot, which we thought was something we could achieve on a multifamily scale. I think you guys, the Shape probably said there's no way that's going to happen. I think we gave them a price and they were like, for 1 unit or for 2 units. So we were way off on that. I would say in terms of what we did end up building it for, we were about 440 a square foot. But that wasn't passive house driven necessarily. We said airtightness, passive house certified, and we don't really care what it costs. Let's figure out what this is. There were no comparisons to look at. There was nobody to ask, what does it cost to build a duplex in Inglewood and certify it passive? The cost savings that we would have gained from multifamily, we didn't gain because it was only 2 units. So, we had a quarter of each building was shared. But if you do that on a scale of 8 units stacked up next to each other, that magnifies. So the cost savings at 2 wasn't significant. We also built it as a row home, so we were able to scale up the firewall we built, and the way we built it was scalable up to as many units as you wanted in a row. So we didn't even take advantage of sort of the code changes or the cost savings we could have as it was a duplex, and the codes are a little bit more lenient on that. So the cost savings for us weren't our main driving factor. We wanted to certify, and because of that, I don't think we really gained a whole lot of cost savings due to it. And the cost increase from passive was minor, but it was a sort of higher end custom single family, or multifamily, small multifamily. So we didn't gain a whole lot of cost savings on it.
So you paid for your schooling, really, right?
Yeah, exactly. So we went into this trying to make money, and we sold 1 unit, and we'll probably about break even. So, but it's well worth it.
Great. Learning curve experience,
Learning curve.
I'd say. Good to know. Now, the Handel Stephen Winters team, this is a hypothetical, but you guys have built this and you have got good costs. And so the question I have for you in terms of costs, can you speculate approximate costs? You guys have moving out west here, and I'm sure potential clients are asking you this question. Got any
Yeah.
estimates?
I mean, we weren't thinking about it until you asked us the question a couple of days ago, and then we started, racking our heads together. So in San Francisco, it's basically on the insulation side, it's code compliant, so that's cost neutral. The addition of the ERV is what we see as the cost, and it's not really from an energy perspective. It's purely from health and wellness and healthy filtered fresh air. And so I think we feel that that's really the only additional cost, which when spread across 85 units isn't that bad. In Denver, though, we are assuming when we're comparing this to a code building, not the New York building that we did, just because labor and material costs in New York are very high, and so it's kind of hard to judge. But we are looking at triple glazed windows in Denver. We're looking at the ERV and additional insulation. And so there's additional cost. What we're thinking there, though, is that it's because of the experience of the team. We're assuming that we would use a lot. You see that as teams do more projects, more passive house, that percentage change is getting smaller and smaller. Mm-hmm. Right now, it's really the ERV mechanical system, and it's the windows, and it's amounting it always comes in about 1% to 2% with an experienced team until the code is catching up. And so we anticipate that would be the same here for multifamily in Denver. And it's not just the design team, it's also the contractors as they get used to it. So maybe the first one in Denver at that scale may come up a little bit higher, and then those contractors know what they're doing. There's less of a kind of the scare factor in their GMP and everything, and then that'll start to rationalize. Hopefully we'll get to like the Pennsylvania Litex stuff where everything starts to be equal or even better.
And what about the air sealing costs? Because I know in San Francisco, for multifamily, the air tightness, theoretical, it's not required to be tested. 7 air changes per hour is code compliant. And so when I bring a multifamily discussion in San Francisco, they're like, oh my God, we can't afford the air tightness. So tell us, what cost would that be to do, because that's a big difference in San Francisco is, as you said, air tightness and HRVs.
I mean, I don't think so. I mean, yeah, people are going to think the sticker shock on it, but like a lot of times we pair Passive House up with like a more prescriptive path, like a LEED or an enterprise green communities, and that you have to do compartmentalization anyway. And so there's already air sealing on the job, and now we're just making sure, like we want that QA/QC on the window, on the facade. That's the additional part. But when you're dealing with the scale of 85 units, you're spreading out that cost. You're getting the advantage of the QA/QC, and so it may be marginally more expensive, but it kind of comes out in the wash.
Nice.
Yeah, and I think on Sendero, I mean, we weren't using any system that was different than, we were using a Henry air barrier. It's a system that, that contractor would have been using elsewhere. We were using the Stowe, the Stowe Gold on the EFIS part. The Henry was on the brick part. But yeah, this was not a kind of unique product. It was it's really the soft cost side of things. I mean, having Dylan and his team on site, talking to the guys at the very beginning, inspecting it as they're moving forward. And really, I mean, I think we definitely saw it on the builders side, on the L&M builders side. When we were talking to these guys, they're excited about it. They want to find the holes. They want to, they're calling us, telling us, oh, hey, we spotted this, we got it taken care of. It becomes a real collaborative team effort, I think, because everybody wants to do a good job. I mean, you want to be, yeah.
One thing to add on that too, with Sendero Verde, there's a really interesting evolution that we can see from the B building to the A building. And the A building, which is going up now, it's actually almost finished, has gone so much more smoothly because we've gone through the growing pains. And the contractor knows what we're going to say and knows what we're going to yell about. So that's really, the first one actually really helps also bring down that scare factor cost potential.
It's great to hear. I know I always love telling the story of going to visit the house at Cornell Tech when it was under construction, and the tour had the crew installing the panels, and they were so proud of their detailing and the fact that they'd worked with Handel to develop the air sealing detail. That story was always. And
on that, I just want to say we take pride. We kind of demand it. Our clients want this. We want the contractors involved as early as possible. With Sendero Verde, with Cornell Tech, we had pre-construction services with the construction teams, and so they were on board. And we had our SD set. They were pricing it and giving us constructability, comments, and so it's really they drink the Kool-Aid along with us.
Absolutely, and you could tell that from the site visit. Now, I'll come to audience questions later. We will keep those for you, but I wanted to bring this air tightness discussion back to our team here from Shape. I always tell architects that air tightness is an architect's responsibility, and your details were beautifully connected. But tell me, Peter and Morgan, you made it possible for Peter's details to connect from the architectural drawings, which were really lovely, by the way. Peter, you did talk a little bit in your presentation about the air tightness, and was there cost associated? I know you went back to get better than. Maybe that was part of your cost. Just give us a little bit background about that.
Yeah, so I think that there's an important distinction to make. So when we're comparing Passive House to other buildings, if you have a really nice code-built building, that's significantly better than what's usually built. Especially here in Denver, air tightness isn't a thing. It's never been a thing. I'm from Maine originally, and if you had a leak in Maine or you had a gap around your window, it started molding within 2 months. Out here, we'll open up windows and they're wide open. Nothing sealing them. There's no situation in which anything came out. There's some bugs nest in there, but nobody cares. With the question of the detailing and the air sealing, I think a lot of projects in the residential world don't have details for air sealing at all. It's caulk here, and it meets minimum code and the building department approves it. What these guys are talking about in terms of, if you're building 100 units, that's a way different standard. There are significant amounts of energy put into and significant amount of money put into planning that out and air sealing. I would probably, as a builder, say it is 100% the builder or the contractor's responsibility to achieve air tightness. Because if even a detail that says caulk around the window, if you do that perfectly, you've got a lot of air tightness. And buildings don't have air tightness, so you got to wonder why we're even having this discussion. It's in my eyes usually a poorly executed project. Putting a line that says this is where you need to seal is very simple. Executing that and dealing with construction debris and rain and mud and contractors is very difficult.
Yeah. So, Ryan, you also mentioned when you're pitching passive house projects in California, the eyes sort of lit up when you started talking about smoke and fire. And I've found also, air tightness in a mild climate doesn't really give you any energy benefits. But when you start talking about smoke tightness and out west, this is key. This is a sales tool, and it's a feature that you're really finding like people want that. And if this is maybe Dylan, you could talk to the impact of that on the mechanical systems efficiency and being able to maintain that boundary between interior and exterior with the air tightness benefit.
Yeah, I mean, there's a real value to something like air tightness and balanced ventilation with filtration that isn't 100% about energy. And I think that's extremely real and getting more real. As far as the sort of maintenance side of it, I mean, I think it one comes back to, I think, the key decision between whether or not you go with a unitized ventilation system versus a central ventilation system. For multifamily specifically, there's a mention earlier about the challenges with a unitized system in a multifamily building, particularly affordable housing. This can get even more exacerbated, where you can't get in every apartment and change filters, and you have to change filters, like especially due to smoke events. Like we had, obviously the crazy photos of New York City earlier this year when the Canadian wildfires were coming down. Like we had a couple projects check their central ERVs, and they were just completely gunked up, as you would expect. So I think with that mindset, as far as keeping smoke out, keeping your filtration system working properly, the decision between central versus decentral is really key. I think central is probably a safer bet to be able to rely on maintenance staff to go check filters, change them if needed. So that's a really, really key component, because we are building airtight. We're talking about the lungs of the building being the ventilation system, and filtration being one of the most key components of that.
And when you're talking about the central ERV system and air tightness, it's not just air tightness from the outside, it's air tightness inside too with the ductworks network. So we used AeroSeal on this project, and we've used AeroSeal on all our projects. I think it's a great system. We have found it to be very effective. But another marketing standpoint, in the age of COVID here, leaky ducts, all the smells and air from one apartment to another are kind of drifting about. I know in the unit that I live in is a 100-year-old building. It's definitely not a passive house. I get to smell everything my neighbors are cooking. So, that's another side of it, making sure that it's airtight on the interior as well.
Good point on the smell transfer. And just going back, keeping on this airtight thing before I get to the next part of costs. Dylan, thanks for running that tighter building airtightness for your model, because I've really seen over and over in harsher climates getting to a much lower than 0.6 airtightness testing number really does make a big difference on your energy. But as you mentioned, Ryan, in colder climates where, or who was it? Maybe it was you, Peter, I beg your pardon, in Maine, you really know when you've got a leaky building in a super cold climate. So, almost it's a de facto durability benefit too. So moving on, just one other details question I wanted to pitch to both teams. I'm a window geek, so I think everybody always wants to know. It's kind of one of the issues that we all are still wanting to know which windows, where do you get the windows? Who did you go with? So just wanted to hear from Shape, what window package did you guys go with? And, feel free to name names.
Only the good stuff. So we went with an Alpen Tyrol series triple pane thin glass. I think we got thin glass. We have a combination of thin glass and true triples. So just a thinner pane of glass in the middle. And we have tilt turn operable windows.
Nice. Made in Colorado, and they're a sponsor of our conference. So shout out to Alphen. And so the Handel team, did you have, look at different cost optimized window packages? And you showed us you went with the UPVCs. Can you share a little bit more about the window selection process?
So for the B building, Intis, the E-Forte system,
Supera.
or Supera, sorry. And then for the tower building A, that was a Schuko system.
And we were, both Dylan and I were very involved in the bid process early on. All the window, we went out to bid early. We got all the bid packages. We sat in bid meetings with each team, making sure everyone understood, because it was, a really critical part. I think about half of them didn't believe that we were going to be able to achieve the numbers that we were targeting. But Dylan was steadfast, and we ended up finding the right solutions. But definitely getting them involved early, I think, is a lesson we've heard 100 times at this conference. I mean, you really need everyone, as many people involved early as possible.
Great. No, I think windows are always like this, biggest cost number in a lot of my projects, even at single family. And as you scale it, it's still relatively high dollar number. So, and lastly, touching on that quad pane in the higher altitudes, Colorado, that did make a difference on the numbers. And I'm putting a plug in here. That's a product in Colorado. You have a climate zone 7. You need that, and there's one manufacturer I know who's making that for this market here. But we really could do with more, and hopefully that'll start to happen with policy changes. So I guess that's, we're not really going to be able to talk too much, unfortunately, about like how to scale multifamily out west here. Can I get a last sort of point for you guys? Where are the opportunities in terms of multifamily scaling out west that we think we should all be tapping, and how do we get that moving?
I'll start. Just it gets easier after the first one. So buckle up and know that that's the hardest one. And then after that, smooth sailing.
Yeah, I think Sendero Verde was part of a competition that included funding from NYSERDA, so that it was a Buildings of Excellence winner. There was a lot of incentives behind that project that made it possible. It was a pilot project to make it more feasible in the future. Now HPD, the Department of Housing Preservation and Development, has an initiative called the Future of Housing Initiative, where they're giving funding specifically to passive house buildings because they've proved out that it worked on Sendero Verde and a variety of other projects that you've heard about. So that's a huge thing. And actually, if we can throw that last slide up again, I encourage everybody to go to this. Dylan did a fantastic tour of the building. So to get an experience of like what this building's like on the inside, I believe there were some images of the facade testing and kind of the process there. Really, really great stuff there. There's also a couple of presentations less exciting presentations that Ryan and I did to give a little bit more context to the project. So
We'll stick around for questions afterwards too, in case there's anyone who has them.
And for the Shape team, where are you going with multifamily in Colorado from here?
I would say, the policy changes and the Excel grants that have come through for the Marshall Fire have been kind of a game changer on the Front Range. There's been a big momentum change with that, mostly in single family, but with multifamily, I think we're seeing a lot of opportunity in the mountain towns of Colorado too, where the climate's harsher. Materials and builders are harder to come by. So there's the prefab options that are out there make more sense. So we're excited about that area.
I think the one last follow-up and conclusion I'd like to say is talk about it. We talked a lot about airtightness. We talked about windows. And I think the thing that sometimes this passive house group misses is how to get a single person to buy into passive house. There are plenty of people in this world who don't care about the environment at all. I think with airtightness, what you can do right off the bat is you can pitch to people, this house is going to make you die less fast. And that's a pretty good sales pitch to everybody.
It is the Wild West.
You don't go outside in the middle of a fire because the smoke, it kills you. We know that. Ozone kills you. All these things kill you, and we filter them out. And if we have air tightness in our house, we can make our clients die less fast. And so that's a pretty easy way to pitch passive house. And in Denver right now, we're trying to pitch passive house. We're trying to get people excited about it because these projects, if we put 100 units in Denver, great. What is passive house is going to be the first question. And so that's a quick way to do it.
I think you got your slogan for next year's conference.
There we go.
Die less fast.
Well, thank you everybody for this. One last announcement. Passive House California, with the help of our board director here, the Oris Group, and Passive House Network, has got multifamily modeling support approved to use the CEDA program, California Energy Design Assistance Program. You will get your modeling process supported through that utility-funded program in California. So really good opportunities. We're working at the policy level to make that happen across the rest of the West. So thank you for joining us, and I really look forward to seeing these projects built the next time we're here in Denver. So with that, handing back to you, but remember to join us upstairs for our happy hour and our closing. Thank you very much.